here we're going to do what are known as initial value problems. Now, remember, when we did an indefinite integral, it gave us a family of functions. So the indefinite integral of f, lowercase f, is given by an antiderivative plus any constant, and to represent that we could use any constants, the indefinite integral will give an antiderivative plus a constant c. That is a family of functions. Now, if we had a condition on the antiderivative, that would allow us to find c. And that's what we're doing here. Condition on the antiderivative will let us find c. And we call this an initial value problem because this condition is known as an initial value. So let's do two of them. First, solve the initial value problem. This is another notation for it. Given a derivative, find the actual function y, given this initial value problem. So dy dx is x squared plus 2, y of 0 equals 3. Well, what we're going to do is we'll say that y equals the integral of the derivative. So x squared plus 2. Well, this is an indefinite integral. It's going to give us a family of functions. Which family of functions? Well, I'll do it, I guess, on the next board. A third x cubed plus 2x plus c. So power rule, constant rule, plus c. Well, that's great. We found y. But notice there are many different things this y could be. But this condition here will tell us there's only one thing that y could be. Y of 0 equals 3. Well, that means when x equals 0, y equals 3. So using y of 0 equals 3, we find, well, when x equals 0, y equals 3. So 3 equals the third of 0 plus 2 times 0 plus c. So c equals 3. Well, we found c. Now we actually have to say what y is because we're trying to solve it. We're not just trying to find c. Solving an initial value problem would means we want to find y. So y equals a third x cubed plus 2x, and c equals 3, so plus 3. So that's one way an initial value problem can work. But remember, we have physics quantities, position, velocity, and acceleration. Derivative of position is velocity. Derivative of velocity is acceleration. Well, we can do that backwards, as we do here. So given a velocity function, and a condition on position, find position. Well, before, we were able to go from position to velocity by taking a derivative. Now we can go from velocity to position using an indefinite integral. So let's do that. I could have also said, given acceleration and a condition on velocity, find velocity. I could have also said, given acceleration and a condition on velocity and a condition on position, find position. And to do that, you'd have to go through velocity. So you'd have to do two integrals in that case. But here, we just want to go from velocity to position. So s of t is the integral, indefinite integral of the velocity function, sine of t, not x, plus 3 cosine of t, 3 cosine of t, integrate with respect to t. And what do we get? Well, we need a function whose derivative is sine. So that would be what? Negative cosine plus 3 sine of t plus c. Now we have sines and cosines. Let's just make sure that we don't have the signs wrong. Derivative of cosine is negative sine, so derivative of negative cosine is negative sine, which is positive sine. That's okay. Derivative of sine is cosine, so that's okay. Well, now what do we have? S of pi equals 5. Okay. using s of pi equal 5, we find, what do we find? S of pi equals 5, so 5 equals negative cosine of pi plus 3 sine of pi plus c. So we need cosine and sine of pi. Well, pi is over here. That's point what? Negative 1, 0. Cosine of pi is negative 1. So negative cosine of pi is negative negative 1, which is 1. Sine of pi is 0. So we have negative negative 1 plus 0 plus c. So 5 equals 1 plus c. So c equals 4. Well, now we just need to write what we get for s of t. So s of t is what? Negative cosine of t plus 3 sine of t plus c equals 4, so plus 4. So these initial value problems I could have done last week with the antiderivatives, but I wanted you to get some practice with antiderivatives before doing this. So all we're really doing here is adding to that a condition which allows us to find the constant. That noise you were just hearing, if that microphone picked it up, was the heat. Maybe I'll turn the heat down.